So good afternoon to everyone and good morning to some of you. We will be continuing the discussion on Fourier transforms. This is a brief recap of what we talked last time. We looked at certain properties and examples relating to when a function is shifted along its coordinate, what it amounts to in the Fourier domain, namely a phase gradient without changing the amplitude spectrum. We also looked at correlation, convolution, modulation at some level. We more importantly spent some time last time at how quickly we can or how one can use the minimal knowledge to begin with and figure out the Fourier domain picture with certain ease based on certain specific functions and certain properties. All right, so one point I had missed to stress, which is trap that lots of people have in the past fallen into, particularly in astronomy context. And this is while interpreting the Fourier domain pictures or what a given pattern indicates and what its Fourier domain picture would be. So one point to stress is there is no point-to-point mapping of information from one domain to its Fourier counterpart. And this is to be stressed over and over again because, for example, you've seen the integral, which is every point in a given domain. You will find that it's an integral of all the points in the other domain. Hence, if you find any discrete feature in one domain on a scale, let's say delta x, some feature which has got a width, then it does not necessarily correspond to any discrete contribution at the Fourier component at 1 upon delta x. So this is to be stressed because people have fallen into this trap and misinterpreted certain data to infer something in the other domain. Okay, this having stress, we can remind ourselves of the Fourier pairs that we have been talking about. And again, I stress there is an inverse dependence of the resolution widths or the scales on which variations are seen. You will find that diffraction pattern and aperture distributions are related in this inverse fashion. And so is the brightness distribution and the spatial coherence function, which is the main topic of this course. You will also find other pairs, which are spectrum and temporal coherence function. Temporal coherence function can be also called autocorrelation function in time, and the spectrum when relating to that will be a power spectrum. In general, the spectral response will be dictated by the time window you use, and so the smoothing of the spectrum is decided by the time window. So if you want higher resolution spectrum, you need to take wide enough data and time before you can achieve high resolution spectrum. Relating to one question that was asked about any deeper meaning about the relation between power spectrum and autocorrelation function, both of them turn out to be the matched filtered versions of the information. Essentially, you would normally do match filtering when you know the pattern, when you know a signature, and you look for presence of it by cross-correlating that template pattern with whatever data in which you're seeking presence of that function. Out here, since in the context of astronomy particularly, we have random fluctuations, so there is no a priori knowledge of what that pattern is going to be. And so one uses the same pattern itself as a template, and that results in the self-defined pattern recognition, which amounts to power spectrum in one domain and autocorrelation function in the other domain. So today we're going to talk about coherence and correlation. This is going to be one of the most incoherent lectures in terms of my going to and fro with several things. So please bear with that. We will first address what is internal coherence. And as I said, it can be crisply stated as compactness in phase space. This is Pierre Lacretne's version of describing internal coherence. So we will look at what this phase space we are talking about and what that compactness amounts to in terms of practical examples. Of course, we have been stressing that compactness in one domain implies the inverse scale in the other domain, which will imply coherence across its Fourier domain on scales inverse of the compact scale. We will distinguish between internal coherence and mutual coherence. And we will see how mutual coherence is retained under any kind of linear scaling or translation, some of which we are familiar with, in one of the domains, but it's not as much appreciated in its Fourier counterpart. And correlation is a simple tool to assess coherence or similarity or matching of patterns, and we will retain its significance only to that as a tool. The innate property of any process is captured by the coherence properties, either internal coherence or mutual coherence when we are comparing two sets of data or two sets of information. Now, it's important to appreciate that when I take two things and assess coherence between them, which is necessarily the mutual coherence, you will find sometimes or many times lack of correlation. The simplest example of that is a simple sine and cosine patterns which are orthogonal to each other. And if we were to formally conduct a correlation, you will find the correlation is zero. But I don't think it requires any convincing that they are fully coherent signals with each other. All that it requires is a shift by 90 degrees, and the matching is more than perfect. While incoherence might lead to lack of correlation does not necessarily imply incoherence. There might be hidden coherence, and which we have not explored, and we need to allow for possibilities which make it appear uncorrelated. So we need to account for those possibilities, search for possible shifts and translations and scalings, which when applied correctly, you would see that the coherence will manifest itself, the intrinsic coherence will manifest itself. Except that if there is real incoherence, no matter what you do, you will not be able to produce significant correlation. So what is internal coherence? As we said, it's a compactness in phase space. Ready examples you already know. For example, if you have a point source or unresolved source in the sky, you will find that the wavefront emanating from it, which are basically spherical wavefronts, and in the approximation allowed by the fact that we are at a long distance from the source, we can approximate that to be a plane wavefront for all practical purposes. And so across the wavefront, you will find there is a complete coherence, and the scale of that coherence is given by the inverse of the size of the source. So if there is some delta theta as the width, you will find over 1 upon delta theta is the scale in spatial scale over which the coherence will exist. Similar thing can be said about an unresolved spectral line feature. You will find the signal, the time description of this spectral line signal. For example, if there is a single tone, you will find it is coherent across the entire time span. Similarly, if there is an unresolved temporal feature, if there is a delta function in time, you know that its corresponding spectrum will have coherence across a wide spectral range. A spatial example, which people don't normally encounter, but people looking for global signals in the sky, like the 3° K background, for example, you will find that it has a spatial coherence only at zero spacing, which corresponds to a uniform brightness across the sky. Of course, from the Earth, it's not really visible across the 4 pi steradian, but in principle, yes. And so that is one very special example of compactness in phase space, where the spatial coherence exists only when you're at the same location. As soon as you move or have any non-zero baseline of your interferometer, you will find there is a lack of coherence. But that is a special case, and it can result from only the uniform brightness component of the sky. As we've been saying, all of these examples will have coherence over the widest scales in the other domain, which we just elaborated on. Of course, as a result of the inverse relation and within the constraints of the uncertainty principle. So most internal coherent structure is the one that is compact, at least in one of the domains. Okay, and so it has coherence scale which is widest in the other domain. If you really compute the volume in phase space, and the phase space that we are talking about is basically three dimensional momentum and three position coordinates, and in the standard physics language, if you compute the volume in this six-dimensional space, it will be following the uncertainty principle. The momentum space combinations would lead to about h cube volume. And so when the volume is h cube, you have a high degree of internal coherence. Let's go through quickly the relevant phase space parameters, which we've been talking in the context of our imaging. We, of course, have two angles, two directional parameters defining the position of a given object in the sky or a source of radiation, and they will correspond to basically the transverse components of the momentum vector. So those two momenta are essentially two of the six parameters. And then, of course, so these can be characterized in practice by the xy components of the momentum, and for as I said, referring to an observing, this is with reference to an observing direction along z. The x and y's are transverse components, and they can be related to direction cosines, as you will see in the formulae John has been describing, the L and M tags. Their Fourier counterparts correspond to a 2D position in the observer's plane. That's again, since we are dealing with this particular example, I'm taking specific reference to location in the observer's plane. This is also with reference to a reference location, which can be arbitrary. So these will refer to as equivalents of spatial frequencies, u and v, when in units of wavelength. So these are two angles and two position coordinates in the observer's plane. They form the Fourier pairs, and those make up for the four of the six phase space parameters. The other two, one of them relates to the frequency itself, which has its counterpart as a delay or time or part difference or widths, in whichever way you want to see, depending on the context in which you are referring to. But they are inversely related to each other. And so these are the phase space parameters we are talking about. And all the constraints that we will invoke and the compactness considerations that we'll have will be referring to these six parameters. As you will find in the context of imaging and the mutual spatial coherence, the relative locations are important, not the absolute location. And as you can appreciate that the absolute locations might only change the phase relation once, and once you have that, in any case, one doesn't know the phase of the radiation in any absolute way. It's a function of lots of things, none of which are under our control except our location. So the relative location is important in assessing mutual coherence. You will find that each one of these pairs, Fourier pairs that I mentioned, even the momentum component in the x direction and the x separation in the observer's plane, are the pairs which will relate to each other. And they will have their own constraints in terms of uncertainty principle, in terms of the ambiguities or the accuracy with which any one of them or simultaneous definitions can be given for the pair. This is one beautiful example of how the simple consideration of uncertainty principle and this inverse relation can be invoked to even derive your familiar diffraction formula without needing any diffraction theory to be invoked. So take a telescope with, let's say, extent of delta x in the x direction, which is orthogonal to the direction of propagation, which is along z, and ask what is the uncertainty in the photon arrival position. As you know, we collect light falling on this aperture across the dimension, across the width d. We don't ask exactly where the photon fell. So we allow for uncertainty in the position, and that gains us beneficially an ability to constrain the direction from which the photon came. And you can actually go through this example in only few steps that you can do for yourself. One assumption here is the wavelength is fixed or the frequency is fixed, and the uncertainty is allowed only in the angle. So you will find that You can compute the component of momentum in the x direction and ask what the uncertainty in that would be, and relate that uncertainty only in the angle. And you will find with a little bit of simple maths, you will arrive at this ambiguity in the direction given by lambda upon the aperture dimension. Same thing can be done in the y direction, which is also one of the transverse directions. And if the aperture was of different size, you will get the corresponding size dictating the ambiguity function in angle. You can do the same thing along the path of the photon. And why I'm stressing this is these are considerations even relevant for even a single photon case. So you can take a column along the longitudinal path of the photon and ask if there is uncertainty over some delta z, I do not know where the photon is, what is the accuracy to which I can define its frequency. And you will find, again, simple manipulation will give you another important relation of delta nu. Uncertainty in frequency is given by the length of the column that you take in units of time. This is something that you are very familiar with. I'm touching upon these to stress the points of what our basic agenda has been. We would like to measure the intensity, which can be in the radio context, just variance of noise that we receive, or in the context where you're counting photons, the number of photons. These we would like to know as a function of the sky coordinates, which adds two more parameters. We would like to know what the color of it is, or frequency, or wavelength. And we would like to see if these things are stationary or constant as a function of time, or varying as a function of time. So instead of taking a still picture, we would like to have a movie, in which case time becomes another axis. And we will not go into the detail of this other parameter, polarization state, presently. But in principle, if we have spans and resolutions in these 6 parameters, it makes about 12 numbers, and they basically define an instrument for us. So whenever you compare one instrument with the other, this is what you are essentially comparing, what the capabilities of the instrument specified in terms of spans and resolutions. But as you know, our grid is contained by the uncertainty relation, and so we are not allowed to specify at will fineness in certain domains simultaneously beyond a certain point. For example, the span and resolution in intensity, which is called the dynamic range, it depends on the aperture area, the spectral bandwidth that you have, the observing time over which you collect the number of photons, and of course, the sky coverage and angular resolution depends on the collecting area and the frequency. Similarly, the frequency, in frequency, the resolution is limited by the inverse of the time span, and the time resolution is limited to how much spectrum we are looking at, what is the width of the spectral span. It's important to appreciate that there are two kinds of bandwidths here. One is the very familiar one, which is the temporal frequencies spread, which we define as C upon lambda, where again the inverse relationships that I will not go through but mention only for completeness. There is also spatial frequencies, which are nothing but equivalents of Ripley patterns on the plane of the sky, and they corresponding frequency description, but these are in space. And so these are defined in units of physical separations, distance between any 2 points, and scaled by wavelength. Because of the lambda dependence, you will find the spatial frequencies depend also on the temporal frequencies, but not vice versa. Now, this is sort of mentioning for completeness. I don't want to go into derivation of the basic theorems, which John is going to do, has already begun. But I just want to illustrate something that in the process of our desire to measure the sky distribution with the finest resolution, we would like to have a huge telescope. And that huge telescope may or may not be realizable in practice. Certainly, it becomes impossible to do so at radio frequencies, and even at optical wavelengths is non-trivial. One can ask actually what one is measuring in terms of what one actually desires to measure. And so what if we had an imaginary telescope which is of the size that we want, such a way that we have the angular resolution that we desire, we will find at the focus we will have the electromagnetic field components converging through either a lens like arrangement or a shaped paraboloid. So at that focus, you can imagine the contribution from different parts of the aperture are contributing, and they're contributing in phase at the central location, and at any other location from the central focus point in the focal plane, you will find they arrive with predictable shifts in phase. So let's look at the central location, and the total electric field can be simply written as a sum of the electric field contribution from each one of these pieces of the imaginary big telescope. And what we are interested in is the E total square, which is the intensity, E total modulus square, given the complex nature of the electric field. And so essentially it amounts to multiplying the E total by its complex conjugate. And your simple maths will tell you that it will amount to summation, a grand summation of series of terms, each one of them of the nature Ei, Ej, where I and J correspond to the two different locations across this imaginary aperture. And what we want is this quantity, but this can be gotten by this grand sum of pairwise products of electric field coming from or received from different patches or sub apertures in this grand imaginary big aperture. And this is the origin of how the pairwise measurements of similarity lead to the synthesizing a big aperture in the process. Of course, having gotten these pairs, you will find that for a different direction in the focal plane or different location in the focal plane, which amounts to a different direction, you will find the same patches will contribute with predictably different phases. And if we have these pairwise products, we can manipulate the result that we would have, or we can construct another set of sum where the pairs results are shifted by appropriate phases and get the answer for what would be the intensity if radiation was coming from another direction, from away from the central direction. This is another way of not proving, but at least driving home the point why pairwise measurements suffice to make the measurement with the grand aperture. Now, as you will see, that the origin of the pairwise measurement simply comes from the fact that what we have access to or what we collect is the electric field, and the intensity happens to be simply square of the electric field. Now, in principle, one can measure each pair patiently, and assuming nothing in the sky changes as a function of time, we can collect all this information over time with a single pair of apertures, move them with different spacings and the baseline orientations, and eventually collect all these measurements and make the grand sum with different phase shifts to get the brightness distribution in the sky in different directions. Of course, within the field of view, which is allowed by each one of the sub-apertures. But if somebody wants to help us, if they give us n such apertures, one can quickly see that we can make NC2 measurements simultaneously, and we can measure these pairs over that. Then we can also use Earth rotation, which allows us the possibility that a given baseline might be viewed by the source with different separations based on the viewing angle of the source. And as you can see, an east west baseline would be viewed with its full extent only when the source is overhead at the meridian, and at the horizon it would see this separation close to zero. And so in principle we can get information about different separations with the same baseline, same physical spacings on the Earth, but viewed differently by the source direction with respect to the source direction. And so this is when that part is used, we call it Earth rotation synthesis. And this is routinely used to get large number of such pairs measured over the span of spacings and orientations. In doing so, to conduct this pairwise comparisons or correlations, we require copies of signals received from the signal received by each one of the apertures. In the radio case, it becomes easy because of ready availability of coherent amplifiers, where we can amplify the signal and make any number of copies we want without degrading the quality of the signal. Whereas that's not the case in the optical, where we need to split the number of photons that we receive and use them. So splitting reduces the signal strength, and it has cost associated with that in terms of signal noise ratio. So what we have talked about is this imaginary big telescope of which we take pairwise subapertures and compute the similarity between signals received at the two locations for all possible pairs that we can think of, which make up the imaginary big aperture. In doing so, we will find that in principle signals received at the two apertures from a given wavefront arrive at different times. And this is something that we will discuss in somewhat detail. But before we go further, we can ask when we compare signals and correlate signals received at the two locations, what do we actually get from the sky? It's easy to show that as much as we are familiar with the diffraction pattern associated with the two-slit optics experiment, we will have a sinusoidal variation of intensity, and this is when we multiply the two signals, this is what it will correspond to. This is not what we do in the young double slit experiment. What we have is a pedestal on top of this, which is also given by individual slit responses, which make the intensity go only positive. But if you were to subtract that and look at the pattern, you will find that it's a sinusoidal pattern modulated by the single slit pattern. And this is the pattern that we actually see multiplying the sky brightness distribution. So if there is a sky distribution like this, when we make a measurement with a baseline B at a wavelength lambda, it is amounting to multiplying the sky with this pattern in the dimension that we have the baseline, in the direction that we have the baseline, and these being constant across the orthogonal direction. So this wavy pattern multiplying the sky distribution and summed over this product is what we get as a final answer. And this is what we call the visibility. You will find that if the source is broad, these ups and downs will be, many of them will exist across the significant brightness, and the net result will be highly reduced. As against a very compact source, which will sample only a small part of this wavy pattern and will attain a value based on where it is seen. Of course, this is only the real part of it, and the imaginary part of it will be orthogonal to it. And so when you measure the complex visibility, you will get the sum of two products, one giving the real part and one giving the imaginary part, where the sky is multiplied by this pattern and its orthogonally shifted pattern with the same ripple spacing. As we said, in doing so, you will find that correlation will be proportional to the intensity of the source, and the real part will be depending on the phase difference that we have based on the direction. There will be arrival time differences, and that would amount to a certain phase shift at a given frequency. And you will find that the fringe spacing is given by lambda by b, or 1 upon u on the plane of the sky, u being the spatial frequency coordinate. And so for a point source, if there was a single point source in the sky, you will find this phase difference can be measured by measuring both the real and imaginary parts of it, which the imaginary part will give sine of the same argument. And by taking tan inverse of this, you will be able to figure out the phase difference. You will find that this can be defined very accurately if we can measure the phase shift. And so essentially astrometry which is also used for geodesy purposes, can actually be more accurate than what the nominal resolution of the telescope or the apparatus might imply. And as was shown in the context of lunar occultation, Peter Scheuer brought home this point for the first time in astronomy context, that you can actually get high accuracy and sometimes even the resolution much higher than what the nominal resolution of the ambiguity function would imply if you had very high signal to noise ratio. And so details of that can be read if people are interested. There's a very famous paper by Peter Scheuer on this. But what we are dealing with while we assess the mutual coherence is the unavoidable part difference in the arrival of the same wavefront at the two locations. So let me get the cursor here. So this is the wavefront. Wavefront is nothing but the equiphase surface. And so when we have radiation coming from any other direction than the vertical, or a direction which is not in the plane perpendicular to the baseline, you will find that there is a finite delay or shift in the amount of added path that the signal has to travel before it gets to the other aperture. And so this is something that we will encounter as an issue to be dealt with. And so we can ask, what is the difference at the two locations, other than this fact that we have arrival time differences of the same wavefront. And this would be even for the central direction when we are looking away from the zenith or from the meridian for east-west baseline. Something which is not talked about often enough, but is a very important point that we have, is that any two locations on the Earth, in principle, would be moving differently with respect to the celestial source. And you will find this motion resulting from the Earth's rotation. You will find the tangential speeds at two locations. Firstly, they will differ depending on the latitude of our place. And of course, the directions are locally tangent. And so it will have the different vectors in principle, and they will also have different projections along the direction of the source. And so we have this situation where we have two observers associated with the two apertures moving at different speeds with respect to the source. And we cannot avoid the Doppler shifts associated with or resulting from this motion. And so when we receive signals at the two locations, we in principle should be warned that even if the same train of things is coming from the source, we are not going to see them as the same pattern because of the change of time axis associated with the Doppler shifts. So this is another difference. So we have differences in the arrival times, that means delays associated with it, which are non-zero. We also have Doppler shifts, which are different. So even for a coherent source in the sky, which is a compact source in the sky, we can ask, do these shifts destroy mutual coherence? Of course, if you blindly compute correlation between these two signals, don't be surprised if you get answer close to zero. And that is because the signals have undergone some predictable but significant changes, which make them look not similar to each other by some blind comparison. But if we know exactly what has happened, we can correct for these. And so as much as we allow for shifts, so one of the definitions I've been told whenever I ask people what they have been taught as a meaning of coherence, they said two things are coherent if the phase shift between them is constant as a function of time. This is a description in, let's say, time domain. You can also have similar description in the Fourier domain, where something was at one frequency, you gave a shift, rigid shift to whatever description existed in the Fourier domain, and shifted it to another frequency. You will find that the internal structure of the information does not change. And so you will find that rigid shifts as well as scalings of the axis. If I stretch one of the axes, the internal information does not change. So it's like taking an apple and shifting its location does not change the internal coherence. And so if we were to compare this, our mind already does that whenever we are shown two photographs where it's a small shift in, let's say, one of the coordinates. We don't take that into account. Our mind allows for that shift and compares only the details. And as long as the details match, we say, yes, it's a coherent piece of information across the two pictures. So same thing is true. Only thing we need to appreciate and stress is all rigid shifts and scalings in either of the domains do not change information. And remember, all these are linear operations. So simple coordinate transformations don't change the information. It's just the definitions and interpretations of it change what you label them as. So intrinsic coherence is not reduced by these operations. I would like to make a bolder statement in this form. You're given some process and it has got some certain property of whatever property of internal coherence or not. You make any copy of it through any reversible transformations of this original thing, you will find that it should be treated as retaining the coherence and having highest level of mutual coherence across the two versions. Because although the correlation might be misleading when you blindly compare these original version with its transformed version through reversible transformations, you may not get encouraging answer about the similarity measure. But if you were to perform the reverse operations to get back what you had and then make the comparison, you will find that nothing is lost in the process. And this is what we actually do. What we do is when we receive radiation at the two locations, blind comparison might be misleading. We might have a frequency shifted version of the original signal because of the Doppler shift. We might have a delayed version of it because of space path, that extra path that things need to travel. But when we correct for these, we will find the true level of coherence, the intrinsic level of coherence popping out in terms of the correlation measure. The actual interferometry involves compensation for all these potential differences and scalings before performing the correlation. And those you can begin to appreciate even more as John will describe of the practical aspects of it. So essentially what we need to do is we want to catch the same wavefront at the two locations. All the efforts are basically that, and the rate at which the wavefronts arrive also to be matched. And so that takes care of both the frequency and the phase shifts. We can take a more fundamental approach, and this was actually proposed by the great John Abel. So once it was unfortunately not implemented in any one of the existing telescopes. If it were to be, a physicist will be at peace in terms of the way these measurements are conducted. And the idea is simple. You have two moving observatories or labs in which we are collecting the information coming from some stationary source in the sky. You can show that what has happened due to the non-zero motion is the definition of time is now different. And so you can take into account all the effects associated with the moving observatory or moving lab and change the definitions appropriately of the clocks and the time and frequency associated with it. And then you will find this is what exactly you have done in compensating for the potential differences of scaling and performing correlation. So we need to recognize that we are on moving labs when we take these measurements and at two different physical locations. And so all the effects associated with shifts and scalings need to be taken into account in both time and frequency domain. So this is something that you will see when we talked about this NC2 pairs. Each one of the pairs in principle over 6 hours of source will measure when it comes from horizon to the the meridian and back to horizon, you will find that each pair is capable of giving you measurements along a typical ellipse. And the two extreme cases of ellipse are, of course, a straight line and a circle, depending on the aspect ratios of the two axes of the ellipse, two orthogonal dimensions of the ellipse. And this is what happens based on the orientation of the baseline. For example, an east-west baseline with a source close to the zero declination, you will find that we sample a straight line track. And so the essential idea is to take all the measurements in this UV domain, in the spatial frequency domain. So it's like covering the space with a felt pen with which we are allowed to draw different ellipses and to cover as much of the area of this imaginary circle that we want to attain as an effective aperture of the synthesized telescope. You will find when we do all these measurements and put them together and take the Fourier transform, it will result in a so-called point spread function, which just one cut is shown here, which may not be as nice single peaked function with width associated with the inverse of the UV span that we have considered. It might have a lot of undesired features called side lobes and so on and so forth. And what essentially we have done is, because of the multiplication associated with the limited number of measurements, so what we have done is unity where we have the measurement and zero elsewhere. This mask is multiplied with the original information that the sky distribution corresponds to in terms of UV domain. And that has been multiplied artificially by places where we admit measurements and where we do not have measurements. And that mask, being multiplication in this domain, amounts to a convolution of the Fourier transform of the mask in the other domain, which is what we see as the point spread function. So it's a convolution of the brightness distribution with this point spread function. And of course, you will see the images you get from this are not as neat looking and clean looking as we desire. That's why this is called a dirty beam, and the images made with such beams in practice are called dirty images. There are deconvolution procedures and so on, which were also used in the initial phases of Hubble when it had developed some distortion, which was corrected later.